And hello all, welcome to week 8, the assignment for May 11th, Monday. Mr. Callan here to help you with reviewing what we should have already learned, rational and irrational numbers. Going to click on the assignment in Google Classroom and note that it is due a week from now, although many of you can get it done pretty simply within today or by tomorrow. Reading today's overview, optional stuff, including a Khan Academy video. If you learn better from Khan, so be it. Let's just learn and grow. Also going to have another experimental live teaching session. Same code this time because I worried that one class ran over and the other class wasn't able to join up. So Callan1234 at meet.google.com. You're watching the video right now. And then the backside is the homework for today. Let's go to that overview for the day. Again, this is from Monday, May 11th, and the objective, I will determine if a number is either rational or irrational, and I should be able to justify my reasoning. So we're going to briefly review different kinds of numbers, why we have different kinds of numbers, and determine then if either a number is rational or irrational. Going to start by talking about numbers, and of course, we use numbers all the time to measure quantities, whether it's amount of money, amount of water in a swimming pool, whatever have you. Now, there are numbers that we can use and then compare rather easily. We can also compute these numbers, but let's just talk about comparing. Let's say you want to compare 2/3 and 11/15. Well, pretty easy when you can get them to common denominators and then find quickly that since 10 is smaller than 11/15, that 2/3 is smaller than 11/15. Furthermore, we can do that if we write numbers in decimal form, and I like to write a little 0 there. Pretty easy to see at that point that while they both have 3 wholes, they both have 2/10. One has hundredths and the other does not, and therefore one is greater than the other. Not only can we compare numbers, but we can also compute them, adding, subtracting, multiplying, dividing. In this case, I would have changed one set to the same style of number, classification of number. You can change them both to fractions or both to decimals. A lot of students seem to be more comfortable with decimals. But what happens when you have these mysterious numbers that cannot easily be changed to either ratios, fractions, or decimals? For instance, many of you could recall right triangles and Pythagorean theorem. Let's say you have a missing piece, the C value, and you find that it's the square root of 74. Okay, what on earth does that mean? And how do we know or even check to see if that's a reasonable answer or not? For instance, many of us can look at 5 and 7 and just kind of estimate a side length of 8. But okay, is the square root of 74 a reasonable answer or not? So these mysterious numbers, that's where we're heading. In fact, today we're just going to describe numbers as either rational or irrational. And then in the next few days, we're going to find a way to come up with, if some crazy number is irrational, we're going to find a way to make a rational estimate. Now, to briefly review something that you might recall seeing in our classroom, I called it our Kingdom of Number bulletin board. And remember, we naturally learn how to count numbers on our fingers. One finger, two finger, we're 3 years old. Then slowly we learn that you can have no cookies. That's a 0, so that's called whole numbers. All natural numbers are also whole numbers, but not all whole numbers are natural because 0, little kids, real young kids don't understand what 0 is like for a few years. Then we learned that numbers, natural and whole numbers can have opposites. So 1 has an opposite of -1 and 2 has an opposite of -2. All those numbers are integers. They have no parts, they have no pieces, they have no portions. Eventually we learn, you know what? Sometimes you have parts, pieces, and portions. And so we started calling those rational numbers if the parts, pieces, and portions can be written as ratios. So for instance, if you look at the lighter blue on the left side, 3.2 repeated, 1 5/10, 2/3, or -2 and 789 thousandths. But you know what? Some numbers have parts, pieces, and portions that cannot be written as ratios. For instance, pi is probably the most famous, 3.14159 ... 0.234709, or -1.460427 ... even the opposite of pi. These are numbers that are crazy, that are ugly, that are not rational, so we call them irrational numbers. And of course, we do have numbers that are not even real. If you look over here on the right side, you're going to see numbers like you can't split 16 into 0 parts. That's impossible. Or the square root of negative 25. What number times itself is equal to a negative? No, you can't do that either. So there are numbers out there that really are made up and don't exist in the real world as we know it. So those numbers are not real at all. But our focus for the next couple years is going to be on real numbers, and today's focus is going to be determining if numbers are either rational and can be written as a ratio, or irrational and cannot. So let's head to today's assignment. Please notice that it has a front page and a back page, but I'm about to do the entire front side with you. So really only the back side is your homework. Your focus, the directions say determine if the number is rational or irrational. But guess what? Anybody can guess right half the time because all you have to do is write rational, irrational. So what I'm going to ask you to do is not just label them, but to prove it. In other words, we should be able to come up with mathematical proofs with numbers and symbols, or with verbal proofs using words. I have placed a nice little word bank up in the top right-hand corner if that helps you with the verbal proofs later on. Let's take a look at the example 1 and determine if the square root of 144 is rational or irrational. Now, the very first thing I'm going to do is say, okay, square root of 144, can I simplify that? Can I evaluate it? And I know that the square root of 144 is exactly 12. Now, I could easily take any natural number and turn it into a ratio by writing a 1 under it. 12 divided by 1 is still 12 wholes. Therefore, immediately I can identify that the square root of 144 is a rational number. So I'm going to use that terminology as I sit here and write in a verbal proof and say any natural number. You could have said whole number or integer as well, but natural number is the best description of this. Any natural number can be rewritten as a ratio. And so now not only have we correctly determined if it's rational or irrational, but we've also proved it. We've proved it with numbers and symbols. 12 over 1 looks like a ratio. And we proved it with words. Any natural number can be rewritten as a ratio. So let's go on to example 2. For example 2, we're asked to determine about pi. Well, we kind of briefly just talked about that. Pi being a ratio of a circumference and a diameter. You might hear the ratio, but unfortunately, we don't know if pi has an ending, nor have we been able to find a repeating pattern to it. So you might have immediately identified, okay, pi, I know that's irrational. But how do you prove that? You prove that with the numbers and with the symbols. We will note that 3.1415, none of those numbers have a repeating pattern, and yes, we better make sure to put that ... at the end to show that it is both non-terminating and non-repeating. And guess what? That is our verbal proof right there. I'm simply going to write pi is both non-terminating and non-repeating, and anytime you have that, no ratio for us. Now, speaking of decimals, let's go on to example 3. Example 3 has 0.3131 ... Wait a second. I feel like that is a ratio or a rational number. Why is that? Well, now we can use those skills that we just learned in the last few days, and I'm going to write an equation where n equals 0.3131 ... And now I can turn this into a rational number by multiplying by 100 because there are 2 repeating digits. So we have 100 times n, 100 n's, and we have 100 times 0.31, which gives us 31 wholes, 0.3131 ... Now we have 2 different equations. As long as we're fair to both sides, we can go ahead and find what this ratio is. Let's go ahead and subtract them, giving us 99 n's and 31, where the 3's and the 1's all cancel out. And of course, to solve for a single n, let's split it up into 99 parts. And we now found a ratio where n equals 31 to 99. That is how we use numbers and symbols to prove that 0.31 repeated is in fact able to be turned into a ratio. Now I can copy my reasoning for example 1, but I'm going to erase the word natural numbers, and I'm going to write any repeating decimal as long as it repeats. can be rewritten as a ratio, and we just showed that with 0.3 repeated as 31/99. Onward we move to example 4, where we have another decimal that goes on forever, but check this out. 6.2579114 ... It doesn't seem to have a repeating pattern. Therefore, what we're able to say is that this number is not rational, it is irrational. And how do we do this? Well, I'm just going to go ahead and select and copy what we have up here and just get rid of the word pi and say that the decimal or the number is non-terminating and non-repeating. And so we can just once again use that non-terminating, non-repeating example or proof. Let's keep on marching along, shall we? -29 we think is rational. Why is it rational? Prove that -29 can be written as a ratio. Well, I can rewrite it as -29/1. Anything divided by 1 is itself. And boom, there is a rational number. And so I can borrow the verbal proof from above, but I'm going to get rid of repeating decimal and write integer. If I can spell correctly. Notice it's not a whole number, it's not a natural number. Little kids don't understand the opposite or negatives. They don't know about owing money or being underwater. But we know that a number can have an opposite. So any integer can be rewritten as a ratio. And now we go onward to example 6, where we have the square root of 40. And I ask myself, do I know what the square root of 40 is? In this case, I don't. I know the square root of 49 is 7. I know the square root of 36 is 6, but I don't know what the square root of 40 is. So I turn to my trusty calculator, where we have a rather lengthy decimal here. And I got my hopes up that it was repeating for a bit. 6.324555, nope, 32. And guess what? If the calculator runs out of spaces, then chances are the probability is almost 100% that it will go on forever. So what we have here is a crazy, ugly, irrational number. And how can we show that in words? By simply borrowing from above. I'm going to simply copy on down and point out that the decimal, you could write the square root in this case is non-terminating and non-repeating. Now, as we go on, I should point out that you folks should be finding some similarities and differences. How are all the rational numbers similar? How are all the irrational numbers different to those? Let's take a look at example number 7. In example number 7, we have the number 1 whole and 2/5. Now, that's a mixed number. Can we rewrite it as a ratio, a comparison of two things? And in this case, you can always take this and change it to an improper fraction, but 7 to 5, that's a ratio. So we can know immediately that 1 2/5 is a rational number. And we'll simply borrow the verbal proof from the top, but now this is not an integer. It does have parts. But we can say that any mixed number, if it has whole numbers and part numbers, which is why it's called mixed, any mixed number can be rewritten as a ratio, just simply changing it to its improper fraction. So at this point, to review, if you think about how all those rational numbers, how are they all similar? Well, all rational numbers can be written as a ratio. We showed that with natural or whole numbers, 12/1. We showed that with repeating decimals, 31/99. We showed it with integers, -29/1, and we showed it with mixed numbers. So again, you can use the word bank up top to write that any natural number, whole number, integer, any repeating decimal, any terminating decimal, which I didn't give any examples of this, is able to be written as a ratio. And how are they different to irrational numbers? Well, we can see quickly that any irrational numbers have numbers that do not terminate and do not repeat. For example, pi didn't stop, didn't repeat. Example 4, 6.2579114 ... non-terminating, non-repeating. And then we had one of those ugly square root of 40, where once again, it does not terminate, does not repeat. So folks, go ahead and take that knowledge with you as you go on to the back page. Again, front page is all my examples. You're welcome to copy mine down or try it on your own and then check my video. Come on back to this video. But the assignment that I'll be working on is on the back page. And don't forget, if you wish, you can kind of color out the little answers that I put. Determine if the given number is rational or irrational, then prove it. Yes, folks, I have popped in some prizes, some numbers that are not even real. In that case, you would simply, I'm not going to tell you the first one is not real, but you would simply say not real, and then you wouldn't put any mathematical or verbal proof there at all. Don't forget to define what that rational number means by looking at its root word. What is a rational number in terms of a ratio? And I have given you the nice word bank to use. You're welcome to use that. All right, folks, do well. If you need my help, just email or message me. Take care. Good luck.